Every 2.4 billion seconds, Halley's Comet swings through the inner solar system, flashes past the Sun, and then vanishes into deep space again. That's roughly 77th Earth years. Not 10, not 1,000, 76 plus or minus a couple of years. For a lump of dirty ice more than 100,000 kilometers from us at closest approach, that kind of cosmic punctuality is suspiciously precise. To understand why Halley returns, we have to stop thinking of comets as wandering fireworks and start thinking like orbital dynamicists. In space, coming back is not an intention, it's geometry plus gravity. Halley's Comet is locked into a closed path around the Sun, an ellipse, just like the planets. The difference is that Halley's ellipse is extreme. At its closest to the Sun, it's perihelion. It dives inside the orbit of Venus, only about 0.6 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. At its farthest, it's aphelion. Halley retreats to about 35 astronomical units, beyond Neptune's orbit and far into the Kuiper Belt region. That stretched out orbit means Halley spends almost all of its time creeping slowly in deep, cold space, and only a tiny fraction screaming through the inner solar system. This speeding up and slowing down is the key. It's Kepler's second law in action. A line drawn from the comet to the Sun sweeps out equal areas in equal times. Translated into everyday language, that means that when Halley is close to the Sun, where the gravitational pull is strongest, it must move faster to conserve angular momentum, its rotational motion around the Sun. Far away, when gravity is weaker, it crawls along. The orbit itself is an ellipse, described by Kepler's first law, with the Sun sitting at one focus, not at the center. For Halley, the shape of that ellipse, how stretched it is described by its eccentricity, about 0.97. 0 would be a perfect circle. 1 would be a parabolic escape trajectory that never returns. Halley sits just shy of that threshold, bound to the Sun, but barely. The orbital period, the 76 years, is dictated by Kepler's third law. This law ties together how far an object is from the Sun. Its semi-major axis, basically half the long axis of the ellipse, with how long it takes to orbit. Raise the semi-major axis to the power of 3, and it's proportional to the square of the orbital period. For Halley, that semi-major axis is about 17.8 astronomical units, and when you plug that into Newton's version of Kepler's law, using the Sun's mass and the gravitational constant, you get a period of around 75 to 76 years. Not because the comet chooses to come back then, but because that's how the numbers of gravity and distance work out. Underlying all of this is Newton's law of universal gravitation, the equation that tells us how the Sun and Halley pull on each other. Every bit of mass in the universe attracts every other bit with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. For Halley, the Sun completely dominates that equation. The Sun is about 2 times 10 kilograms. Halley, by contrast, is on the order of 10 eigensols. That's a factor of 10 quadrillion less massive. So the Sun's gravity dictates the orbit. Once Halley has a particular combination of energy and angular momentum, how fast it's moving and in what direction at a given point, gravity carves out a specific mathematical path, a conic section. If its total energy is negative, it's bound to the Sun and follows either a circle or an ellipse. If the energy is exactly 0, it follows a parabola and never closes back on itself. If the energy is positive, its path is a hyperbola and it never returns. Halley's energy is negative but close to 0. It's like a ball thrown so hard it almost escapes Earth's gravity, but not quite. It rises, slows, and eventually falls back. Halley's long, slow fall back toward the Sun takes decades, but the principle is the same. As long as nothing gives it a big enough gravitational kick to change its total energy from negative to 0 or positive, it will keep looping around the Sun again and again. This is where Halley becomes special among comets. Most of the bright comets humans notice in the sky are what astronomers call long-period comets. Their orbital periods are thousands or even millions of years. Their semi-major axes stretch out to tens of thousands of astronomical units, deep into the Oort cloud, a spherical shell of icy bodies surrounding the solar system. For many of them, we only see them once. Their orbits are so huge that from the perspective of human history, they might as well be single-use visitors. On the other extreme are short-period comets, ones with orbital periods less than about 20 years, often associated with the Kuiper belt. They zip around the Sun relatively frequently, but are usually much dimmer, just faint smudges in a telescope. Halley occupies a strange middle ground. With its 76-year period, it belongs to the class of Halley-type comets, periods between 20 and 200 years. But it's the only one that's both bright enough and predictable enough to have been recorded by so many different cultures over millennia. That's why it became the first comet recognized as periodic by Edmund Halley in 1705. Its orbit is just short enough that you can reasonably hope to see it at most once in a human lifetime, and just stable enough that historical records line up: 1531, 1682, 175, 1835, 1986. The 76-year timing sits right in the sweet spot between astronomical and human timescales. But there's a twist. Halley doesn't orbit the way the planets do. Most planets move around the Sun in the same direction the Sun rotates, which we call prograde motion, and they stay close to the same flat plane, the ecliptic. Halley is a rebel. It moves in a retrograde orbit, meaning it travels around the Sun in the opposite direction, clockwise if you're looking down from above Earth's North Pole, while the planets go counterclockwise. Its orbital plane is tilted by about 162 degrees relative to Earth's. If it was 0 degrees, it would lie in the ecliptic plane like Earth. 90 degrees would mean a polar orbit, plunging above and below the solar system's plane. 162 degrees means it's not just tilted, it's flipped, moving backwards. This geometry matters because it changes the relative speed between Halley and the planets when they pass near each other. Think of two cars on a racetrack. If they're both going in the same direction, even fast cars can pass each other gently. If they're moving in opposite directions, their relative speed is the sum of both speeds, and any encounter is much more dramatic. For Halley, that means that when it crosses the orbits of Earth, Venus, and Mercury, the relative velocities are high, tens of kilometers per second. These high-speed flybys reduce the time it spends near the planets where their gravity can significantly tug on it. So ironically, being a retrograde oddball helps preserve the overall shape of Halley's orbit, keeping it roughly on that 76-year schedule over centuries. Still, roughly 76 years is doing a lot of work. Halley's orbit is not a perfect celestial metronome. Its period has varied from about 74 to 79 years over recorded history. That's because in the real solar system, the Sun is not the only player. The big outer planets, especially Jupiter and Saturn, act like gravitational bullies. When Halley passes through the outer solar system, its trajectory can be nudged by their enormous masses. These are not head-on collisions, of course, but subtle gravitational encounters. As Halley glides past Jupiter's orbit, for example, Jupiter's gravity can either steal a bit of orbital energy or donate some, depending on their relative positions and speed. This process